Hello everyone, let's analyze. So we've built a suite of topological tools, how to describe when a set is compact, open, closed, what an open cover is, what a finite subcover is. We've learned even a little bit about how continuous functions deform compact sets. We know that if a continuous function is applied to a compact set and is continuous everywhere in the compact set, it's automatically uniformly continuous. You get a level up in your scale of how continuous you are. So one of our main goals is to show that continuous images of compact sets are themselves compact. In other words, if you have a continuous function and you apply it to every element of a compact set, then the resulting set that you create by applying f to every entry of a compact set is itself compact. So compactness is not lost when you apply a continuous function. So to get our way there, we're going to show first that the uniformly continuous image of a bounded set is bounded. That is, if f maps E to R is uniformly continuous on E and E is bounded, then f of E is bounded. That's a typo. Should say just is bounded. It looks like I have an Italian accent. F of E is bounded. So let's prove it. Okay, first, apply the definition of uniform continuity with epsilon equals 1. Now, I actually could have picked 7 or 6. I picked 1. Okay, so let epsilon be 1. There is a corresponding delta greater than 0. And if x and y are in the domain E and within delta of each other, then f of x and f of y are within 1 of each other, because I'm choosing epsilon to be 1. Now, since E is bounded and non-empty, well, okay, E is not necessarily non-empty, but if E were empty, the result is vacuously true. So we're not really concerned with the case of a empty domain. So suppose it's not empty and that it's, of course, we assume in the hypothesis of the theorem that E is bounded. That implies that E has an infimum and a supremum. And we could actually take the closed interval from the infimum to the supremum and partition that interval into subintervals, where each subinterval is length delta. In other words, start at the infimum and add delta to it, and then go from the infimum plus delta to the infimum plus 2 delta, and keep going until you get past the supremum. Then, in each of these delta length intervals, I can choose an element of E, xi, and then I could take the delta neighborhood of xi for I equals 1 through n and build an open cover for E. Specifically, a finite open cover. Now, E is not necessarily closed, just bounded. So we are able to cover E with a finite set of open neighborhoods. But remember, not every open cover of E permits a finite subcover, but this one does because we crafted it to do specifically that. We can take the set f of E, which is the set f of x for every x in E, and we can actually contain that in open intervals centered at f of xi with a radius of 1. In other words, a 1 neighborhood of f of xi. Well, how do we know that we can do that? Well, let's consider any element of f of e, right? In order to show that 4 is true, I got to show that that every element of this, or rather any arbitrary element of this, is contained in this. And because that is a union of a finite number of sets, I got to show it's in one of these, because remember, the union is like a or statement. So, given an arbitrary element of this, show that that element is in one of these neighborhoods of f of xi. And recall what f of e is. It's f of some value in the domain. So in fact, we can describe elements of f of e, that is elements in the image, as f of y, where y is in e. So suppose f of y is in f of e. Then y is in a delta neighborhood of xk for some k. Because we covered the domain with delta neighborhoods of xk for k equals 1 through n, and y has to be in one of them. Now if y is in a delta neighborhood of xk, then xk minus y is less than delta in absolute value. Which implies, from this statement here, that if xk minus y is less than delta, f of xk minus f of y is less than 1. Which is precisely the statement we have written here. And that implies that f of y is in the 1 neighborhood of f of xk, which means an arbitrary element of f of e is in one of these 1 neighborhoods of f of xk, which means it's in the union. And because f is contained in a finite set of bounded intervals, f of e is bounded. Right? In fact, it's bounded specifically below by the smallest value of f of xk minus 1, and it's bounded above by the largest value of f of xk plus 1. And that completes our result. And now, the main event. Now we're armed with all that we need to show that the continuous image of a compact set is compact. Compactness is not lost when we apply a function to a compact set if the function is continuous. Now what do we know? What do we know so far? We know that a continuous image of a compact set is necessarily a uniformly continuous image of a compact set. And we know that the image is bounded. We just got through proving that. Now, since a set is compact if and only if it is closed and bounded, thanks for that, Heine-Borel, all that's left to show is that the image is closed, since we just proved the bounded part. So let's give the full theorem. The continuous image of a compact set is compact. That is, if f maps e to r is continuous on E and E is compact, then f of E is compact. Let Z be an accumulation point of f of E. Now, why am I starting there? Right? Why take an accumulation point of f of E and dissect it? Well, remember what our goal is. Our goal is to show that f of E is compact. But we've given ourselves a head start. We know from the theorem we just proved that f of E is bounded. We already know that. We know that compactness is equivalent to a set being closed and bounded. So all we have to do is show that f of E is closed. And we do that by showing that f of E contains all of its accumulation points. So let Z be an arbitrary accumulation point of f of E. Our goal is to show that Z is in f of E, which is true if Z equals f of x for some x in E. Okay, so back to our proof. Let Z be an accumulation point of f of E. then there exists a sequence of elements f of xn of f of e that converge to z. Remember, if z is an accumulation point of f of e, then every neighborhood of z has infinitely many entries of f of e, and from those entries we can construct a sequence that converges to z. So let f of xn be precisely that sequence that converges to z. Now, since the sequence xn is contained in the domain, which is compact, then xn has a subsequence, xn of k, that converges to some value x in E. Now, let's apply f, which is continuous, to this convergent subsequence. Well, continuity buys us the fact that f of x n of k converges to f of x because x n of k converges to x. But f x n of k is a subsequence of f of xn, which converges to z. So we just proved that z is f of x. How did we do that? Well, remember, every subsequence of a convergent sequence, and f of xn is a convergent subsequence, converges to the same point. So if f of xn converges to z, then f xn of k converges to z as well. We know f xn of k converges to f of x, therefore z equals f of x. And since z equals f of x, z is in the image of f of e. Thus, f of e satisfies the definition of a closed set. As it's already bounded by our previous theorem, we have shown that f of e is closed and bounded, which is equivalent to being compact. Thanks again, Heine-Borel. That's it for today.